that it is this group already present on aromatic system that directs the electrophile, either this position, that position, or this position. It is this group, in fact. It is not the nature of electrophile. So this is very well understood. So X may be two kinds. If this X is containing a non-bonding electron pair, just like I have exemplified halogens, oxygen, sulfur, selenium, it may be nitrogen, phosphorus, arsenic, etc. So they are having lone pair present. So what is the effect of this lone pair? This lone pair can be contributed towards resonance. If it is donate this electron pair here, so this pi electronic density shall transfer on this carbon. You see this carbon is becoming electron deficient, electron rich, negatively charged. So this electron density transfers here and this pi electronic density transfer here, generating a negative charge here. Very similar, it generates a negative charge here, then it go back to the same form. You see here, this double bond is here this double bond is not there. So these two, first one and the last one, they are not same. They are two different calculus structure, if you remember. So these are five different resonance forms with this category of X groups. Is not necessary this is oxygen OH. It may be O alkyl group, alkoxy group, all right. So any kind. So but must have a non-bonding electron, at least one. Nitrogen, phosphorus, arsenic has only one. If it is, let's say, oxygen, sulfur, selenium, they shall have two non-bonding electrons. So chlorine, bromine, iodine, they shall have three non-bonding electron pairs. So they shall contribute here and resulting. So if X group is containing a non-bonding electron pair, at least one, it is increasing electronic density at ortho, and this is para. It is not increasing electronic density at these two positions. You see, this position is ortho to this. This position is also ortho to this. This position is para to this X group. So it is increasing electronic density at this position. Electrophile is electron deficient. It shall be attracted electrostatically by this negative charge. Just focus why electrophile approach this position and para position, because there is charge here, negative charge. So electrophile prefers to approach opposite charge. So opposite charge is available at ortho and para, not at meta. That's why electrophile shall not approach this carbon group. It shall approach ortho and para. So it shall result product number 2 and 4. This is the result with this possibility when X is having a non-bonding electron pair. But if X is bonded to a carbon, now this X may be oxygen, this may be sulfur, this may be nitrogen, this may be phosphorus, but cannot be halogen. Halogen doesn't make double bonds, right? It cannot be halogen right now. It may be oxygen, like in carbonyl oxygen. It may be sulfur, like sulfur also forms such type of compound. It may be nitrogen, like in imines, etc. So anyhow, this may be oxygen, sulfur, or nitrogen practically. If it is, then reactivity is totally different. This group is having what impact? It is generating a positive charge on it. If there is a positive charge on this, it means this group is by resonance, this is plus R. Plus R. It is causing increase in electronic density to the aromatic system. It is donating its electronic density to the aromatic system to increase electronic density here. So this is a plus R group. Mean by resonance, it is electron contributor. On the other hand, look at this. If this X is in this fashion, so it shall take this electron pair off. This pi electronic density shall transfer here, generating a positive charge at this position. So this electron density shall transfer to generate a positive charge here, then positive charge here, And then these two forms, first and last, they are not same, they are calculus opposites. So now look at here, what is happening? Totally opposite behavior to the first one. Here at ortho and para, electronic density is increased. Here at ortho position and para position, electron density is decreased. So as a result, we shall conclude that this is causing a decrease in electronic density at ortho and para if electrophile is positively charged. So these ortho and para are also positively charged. So what shall happen? Electrophile shall be repelled by this. So electrophile shall not approach ortho and para position. Where it shall go? Only one possibility is met. This side or that side. Same isomers. So if electrophile is approaching such system, then it shall prefer to go to meta position. This is what product number 3 shall be formed in such a case. Not 2 and 4 shall be formed. So on such basis, we can classify there are two types of X. It may be ortho para director or it may be only meta directors. These are the two categories of the such rings. Now let's see, in next slide I have exemplified these. This is the table which is presenting the X. X when it is 5, when it is 6. What is 5? This is the structure number 5. This is the structure number 6. In 5 case, this X is different. No, we shall have 3 different categories. This may be halogen, this may be oxygen, this may be nitrogen. 3 groups. Nitrogen contain 1 non-bonding electron pair. Phosphorus, arsenic as well. If this X is containing 2 non-bonding electron pair, maybe oxygen, maybe sulfur, maybe selenium. If it has 3 non-bonding electron pair, so it may be chlorine, bromine, iodine, etc. So on such basis, we can classify these 5 model into 3 categories, right? So this is what I have done in this case. So it may be nitrogen, phosphorus, oxygen, sulfur, it may be halogen, etc. If it is observed nitrogen, phosphorus, 1 non-bonding electron pair, oxygen, sulfur, 2 non-bonding electron pair. So due to inductive effect, this is minus I. Minus I means this is electron withdrawing because they are all have electronegativity higher than carbon. So by inductive effect, they shall be minus I, electron withdrawing. And with respect to resonance effect, they are plus R. You have seen already, these are donating electronic density. By resonance, creating negative charge itself, they are getting positively charged. So this is what you have come across. So such groups, nitrogen family and oxygen family, they are minus I but plus R groups. So they are orthopara director. We call them strong activator because in case of nitrogen and phosphorus, they contain only 1 non-bonding electron pair. In case of sulfur and oxygen, they contain 2. There is a competition, so which makes their contribution to aromatic system less. If let's say even nitrogen is more activating than oxygen, all right. So because the nitrogen contain only 1 non-bonding electron, there is no competition at all. It strongly donates this to aromatic system. In case of oxygen, there is a competition. That's why due to this competition, less contribution takes place. So it is a strongly activating. I have exemplified like phenolic entity OH, alkoxy group, SH, SR, NH2, mean unsubstituted amine, monosubstituted amine, disubstituted amine, any of them if present on aromatic system, it shall be strongly activating, mean it shall generate a lot of negative charge on the aromatic system. If it is halogen, let's see, if it is halogen is having 3 non-bonding electron pair, bromine, chlorine and iodine. It shall have 3 non-bonding electron pairs. High competition. As a result, it shall be the very same behavior, minus I. It shall be by resonance effect. So it shall be plus R because it is contributing electron density, and uh, minus I effect by resonance. So by inductive effect, it is withdrawing electronic density. So halogen have a plus R effect, electron donating by resonance, but electron withdrawing by inductive, right? This is ortho para director as well. So halogen, but disadvantage is halogen contribute less. They are not very good orthopara director because they have three non-bonding electron pairs. So as a result, there is a high competition. So it activates to small extent. That's why we call uh, this is a deactivator group because here inductive effect is dominating, resonance effect is recessive. In this case, inductive effect is recessive, resonance effect is dominating. All normally resonance effect dominate over inductive effect. This is true in this case, but this is opposite. Here inductive effect is dominating over resonance effect. That's why this is not activating. If you have a halogen present on aromatic system, it shall be orthopara but deactivator. It shall not activate the ring in fact, right? So X may be chlorine, bromine, or IT. Third category, which have no resonance effects, alkyl group, methyl, ethyl, etc. They have no non-bonding electron pair, so they are not going to contribute. So they are having zero resonance effect. Now, if you look at in previous slide, this is bonded with, if this is carbon, this carbon shall be sp3 hybridized. So sp3 hybridized carbon is always less electronegative than sp2 hybridized. We have seen this already in basic concepts of hybridization, that sp carbon is slightly more electronegative than sp2, and sp2 is slightly more electronegative than sp3. So this is very simple. If it is sp3 hybridized carbon, no non-bonding electron pair, so it is transferring electronic density towards it. Why? Because sp2 hybridized carbon is slightly more electronegative than sp3. So electronic density shall be slightly transferred here, but by inductive effect, not by resonance effect. So this resonance effect shall not be contributing towards this. So only inductive effect is there. So alkyl group is electron donating. It is less electronegative. This is totally opposite, but no resonance effect. It shall also be orthopara director, but it is mild activator. Look at the difference. This is mild activator. This group is strong activator. Halogens are deactivated even. So, but they are having lone pair, different number of lone pair or no lone pair at all. So this is the structure number 5 we have discussed. Now let's see if we are having a model number 6. And model number 6 is this one, in which we have a carbon X double bond. So this X may be oxygen, sulfur, nitrogen, phosphorus. In all cases, it is no doubt by inductive effect, this is electron withdrawing. But by resonance effect is what? It is electron withdrawing as well, not electron donating. If it is withdrawing electronic density, you have seen it is causing a positive charge at ortho and para position. So that's why it is causing meta position to direct this. This is strongly deactivating. Why deactivating? Because this is causing a positive charge on aromatic system. It is deactivating the system. So what it can be? It can be aldehyde, ketone, carboxylic acid, ester, acid halide, acid amide, imine, nitro, carbazide, semi-carbazide, etc. All such functional group it may be, right? Another category, if let's say we have Y group is attached and R number of alkyl groups attached with this. So it is not, it is positively charged already. Heteroatom is positively charged, so it has no resonance effect because it has no non-bonding electron pair present. Fine. So similarly, minus I inductive effect means what? It is withdrawing electronic density. It is electron density withdrawing. So it is strongly deactivator, like if you have a tertiary aminic nitrogen attached, or you are having a simply S group attached to this. Then it shall be strongly deactivating but meta director as well. So these are the orientation of an electrophile. We can classify into 5 different groups. If this is a this 5 model or 6 model in previous slide, alkyl group is present on aromatic system. It shall be ortho para director but mild activator. If it is halogen, it shall be mild deactivator but ortho para director. If it is nitrogen, sulfur, oxygen, phosphorus, etc., it shall be ortho para director but strongly activating. This is the difference among them. But if it is 6 model, oxygen, sulfur, nitrogen, phosphorus, then it shall be a strong deactivator group but meta director. So these two are meta directors, structure 6, structure 5 are orthopara directors. So I don't think so we shall be able to cover this all rules of orientation. So let's see, there are certain rules of orientation. There are so many, but I have selected a few for your convenience. Let's see, just see, go through the very first one, and then we shall see the others in next lecture. First of all, we have just 3-4 minutes remaining, so I shall try to bind just one rule today, and then we shall continue this further. Rule is written: if a strongly activating group competes with a weaker one, a deactivating one, or the former controls the substitution. Former means what? Uh, let's say if I exemplify, this rule shall be understandable to you once I exemplify this. But let's say we have this molecule, a methyl group and a hydroxyl group. These two are present at this position, right? Now OH, if you remember, just go to back slides. If OH is present, oxygen, just like this is strongly activating. If you have an alkyl group, this is mild activator. This is activating it to small extent. This is activating this to a strong extent. So now we have two options. Either this is controlling or this is controlling. It shall control the, this is orthopara director. This is also orthopara director. If it is orthopara, it shall substitute here or there, 2 positions. But if it is methyl, it shall substitute it here and there. So all 4 possible position electrophile has been approaching, but it doesn't happen. One of them control. Which control? The one which is more activating. Competes with a weaker one. If a strongly activating group competes, strongly activating group competes with a weak one or deactivating one. So these are the 2 possibilities. Deactivating, like maybe halogen. So if you are making a comparison between a strongly activating like OH with a weaker or deactivating, just like methyl is a weaker activating, and in this example I have taken nitro in blue color. This is a deactivating group, right? So if you have a comparison between activating, here methoxy is also activating, strongly activating. Here phenolic is strongly activating. Here both of these two are different. This is activating but small extent. This is deactivating in fact. So this is just, I have taken 2 examples just to illustrate depending upon these 2 principles. So in this case, this methyl shall mask out the effect. This OH shall mask out the effect of this methyl. It means this is not going to orientate. It is this OH group which shall be directing this electrophile. At what position? Its one ortho is occupied. It shall orientate it at this position and this para position. So electrophile shall be in structure number 2, either this position or that position. It shall not orientate it at this para position, sorry, meta to OH and meta to OH. It is not meta directed. So this is 2 possible isomers are going to be produced. Second, if it is this case, in this case, activating group is activating here and activating there. Nitro is deactivating these 2 positions. So at these 2 positions, this electrophile shall be repelled off. But at these two positions, there is more electronic density available. So it shall approach at this position or that position. So this is what is the rule first. But now let's see if these two positions are different. In next presentation, I have presented this. If it is only this one, this is the same you have seen in previous. So electrophile shall approach at this position and that position. This shall be major isomer in more concentration than this. Why? Because this position, look at this position, if electrophile is sterically crowded, so these two are not sterically crowded position, it is not sterically crowded. But you see here OH group has lone pair present which shall repel this electrophile. So as a result, this shall be having less contribution towards this. Although two possibilities are there, one is this, other is this. So it should be 50% this, 50% this, but it is not going to work. Here there is steric factor is poor. Here there is a little steric factor. That's why this shall be minor isomer. This shall be a major isomer. Look at here. In this case, the same two groups are present, same two, but their positions are different. Here both of them are ortho. Here both of them are meta. Here both of them are para. In fact, now look at here. If it is this one, now three isomers are possible. One is this. One is that, one is that. These two are ortho and this is para. But electrophile, if approached between the two, this methyl is sterically crowded, this OH is also sterically crowded, this electrophile doesn't approach. We shall see the next rule which is about this. Between the two groups, a new electrophile shall not approach due to steric factors. So this rule you shall see later in next lecture. So it is not going to approach here, two positions remaining. One is this and other one is that. So one is this closer to methyl, other is closer to hydroxyl. But both of these are sterically crowded. So none of them should be major and minor. Both shall be equal. Now let's see if I increase this alkyl group size. If I make it isopropyl or N-butyl, if I increase the size of this, then the concentration of this isomer shall decrease, 5 shall be formed less, and 6 shall be formed more. If let's see, I do the opposite. I increase the size of this group. If I attach a alkyl group here, methyl, ethyl, propyl, as I shall keep increasing the steric factor here, the concentration of 6 shall decrease and 5 shall increase. It depends upon what sizes we are having at these two positions. So the concentration of 5 and 6 shall be dependent upon that. Now let's see if both of these are at two para positions. Now you can see this shall control, but it had two positions, ortho, ortho and para. In this case, either electrophile approach this position or it approach this position, it is identical. If it approach here or there, it shall form the same product. So only one product is possible in this case when the two groups are para to each other. When they are ortho or meta, then there are more isomers are possible in fact. So this is time to time we look into the substituent, what is their position and what is their nature. Both are important towards orientation of new electrophile. So I hope this rule is clear to you that when you are having more than one, when it is one substituent, it is very clear. When it is simple methyl, so it shall be ortho and para. If it is simple OH, it shall be ortho and para. If it is nitro, it shall be only meta. So that is very clear, no doubt about that. You have seen in the previous two slides. But if it is more than one substituent present, one is activating, other is less activating or deactivating, then strongly activating shall always dominate. Let's say if you have a mild activating and a strongly deactivating, right? So mild activating shall dominate over deactivating one. So this is are the some aspects that are very interesting to see, and the position of these two also make a big difference. So this is all about today. We shall continue these rules of orientation in next lecture. So you have another rule. You shall be seeing two other rules. etc. And then we shall focus on the other cargo cycle, ortho para ratio, ortho effect, etc. And I shall suggest you, this is the last slide of this presentation. So chapter 21, you have already read this. I have already made this suggestion in previous week, 473 to 497. I have included a chapter 22, which is about the aromatic nucleophilic substitution reactions. So just read out these things. These are just 13, 14 pages, page 513 to 526. So it shall be very helpful for you to understand this course. So we shall again switch over to the aliphatic substitution reaction, but after completing this, a few slides, that the 4 5 slides which are remaining in this, we shall continue this, and then we shall switch over to aliphatic um, substitution reaction. It may be aliphatic nucleophilic and aliphatic electrophilic substitution reaction. So both we shall cover in upcoming weeks. So if there are any questions, these are welcome.